Thanks for joining us on our 7th lesson of Work, Power and Energy. As said, today we will be discussing mechanical energy. Now, mechanical energy is also underwritten by a law called the law of mechanical energy. And this law basically states that the total mechanical energy in an isolated system stays conserved. Now, although we have discussed isolated and conserved before when we looked at momentum, let's just quickly recap again. Isolated means that there is no external forces involved. And when we do refer to external forces, we refer to forces like friction. So basically, if they tell you that there is no friction present, it means to you an isolated system, and that means you'll be using mechanical energy to do the rest of your calculations. Now, conserved is just another fancy word for the word constant, or the fact that it stayed the same. Now, the formula for mechanical energy is not given on your formula sheet. You would need to go and memorize it. And it basically states that the mechanical energy at the top is equal to the mechanical energy at the bottom. Now, you'll see we refer to top and bottom because in most of your examples you'll have a situation where the object is starting or ending at the top and then either starting or ending at the bottom. Now, mechanical energy is equal to the potential energy and the kinetic energy. Now, when we refer to potential, we're talking about the gravitational potential energy plus the kinetic energy. So therefore, my potential plus kinetic energy at the top is basically equal to the potential plus kinetic energy at the bottom. And we can go and break that even further down because we know gravitational potential energy is known as mgh for mass, gravitational acceleration and height plus a half mv squared. And that will be the same as for at the bottom part. So as said, this formula is not given and you would need to memorize it as well as the breaking down of it. Let us now consider an example. An adult monkey which is sitting on a log at some height above the ground swings on a rope towards its stationary baby on the ground. While swinging, it grabs its baby and continues to swing upwards. Now, a few key points that we need to look at here is the fact that it is sitting on a log initially, our monkey. So if it was sitting, it means that its velocity over that point is 0. And then it's going to swing down a specific height till it reaches its baby at the ground, which he will then pick up and continue swinging forward. Now let us look at a diagram. So our diagram indicates here at A, this is our piece of rope moving upwards. The monkey takes this piece of rope and which he was sitting on a log, that means his velocity there is 0, swings towards his stationary baby at the bottom, so the baby also has a 0 velocity, and note though that he then swings a height of 1,4 meters from the ground until he reaches his baby and continues with the baby upwards. So this height here at A is 1,4 meters basically off the ground. Now the question from here onwards tells us to ignore the effects of air resistance. Now, air resistance also basically refers to friction. So they're basically telling us to ignore friction. Then they want us to state the law of conservation of mechanical energy. Now that says the total mechanical energy in an isolated system stays conserved. Now the second question asks us use the above law then to go and calculate the speed of the adult monkey which has a mass of 5,8 kilograms, just as it reaches its baby, which is a mass of 1.2 kilograms at B. Now when we read our question, we need to make sure that we realize exactly where the monkey is going to be when we need it to calculate its speed. They say to go and calculate the speed of the monkey just as it reaches its baby. That means it has not picked up its baby yet. It is only still the monkey itself swinging from point A to point B. It thus has not picked up his baby yet and therefore would still be the same mass of 5,8 kilograms. So that means your mass here for the baby of 1,2 kilograms you can ignore for this calculation. Now when you have to do the calculation, you've got to go and write out mechanical energy at the top is equal to mechanical energy at the bottom. That on its own is equal to potential energy plus kinetic energy at the top, which is equal to potential and kinetic energy at the bottom, and that is equal to mgh plus a half mv squared at the top, and that's equal to mgh plus a half mv squared at the bottom. Now, I'm not going to rewrite the first two ones for you yet because I don't have enough space to do that with the calculation on my slide, but I will continue with the last formula and then from there onwards add in our values. So seeing that we are only working with the adult monkey, we have then a mass of 5,8, gravitational acceleration of 9,8 there at the top. Now at the top we referred to position A when it was sitting on the log. Its height above the ground we realized was 1,4 meters. Plus, when we go and look at its velocity, it's a half, mass of 5,8, and now note, we said that it was sitting on the log, and therefore its velocity meant it's 0, and this is 0 squared. Now you need to include the 0. You can't just decide to leave out this whole expression because you do get marks for substituting in your values. Now this will be equal to your gravitational kinetic energy at the bottom, which is then still the 5,8, 9,8, but now when it reaches point B, it's basically on the ground. Therefore there is no height above the ground in this case. And there is still a half, mass of 5,8, and we want to go and calculate what is this velocity at the bottom. Now if we go and simplify our calculations from here onwards further, we'll end up with 79,576 plus 0, and that is equal to the 0 plus the 2,9 v squared. So in order to make v the subject of the formula, I'll do the square root, well, take the 79,576 and divide it by the 2,9. And that will give us 5,24 rounded off to 2 decimal places meters per second.